Okay, this is 1.5. This is basically exponential modeling. These are real life situations, so the graphs aren't going to come out as perfect as the last chapter, but we're going to do something similar. The Explorer wants you to take a basketball and drop it, and then it wants you to measure its height. So the idea is they want to put a couple of rulers up here, start with something really, and then put the basketball and drop it and see what the height is after each bounce, which you can't really do here. But so if I drop it from here at 180, they want us to record what's its height after the first bounce, the second bounce, the third bounce, the fourth bounce, the fifth bounce. I'm not going to do that, but you can see that it's going to go down. And they graph something that looks similar to it. And it looked kind of like this. So you know it went down. The question is, how do you know if it's exponential or not? Well, the way you do that is by calculating the ratio between the two, just like we did before. If I do the ratio between the first two, so divide the second one, divide by the second one by the first one, get the ratio. Divide the third one by the second one, get the ratio. Divide by the fourth one, divide by the third, that one, divide by that one. And we find the ratios, just like we did on the tables. Okay? But again, as always, life is not so simple. So as we scan down, we'll find another one. Let me scroll here for just a second. And they give us this right here. All right, now again, there's a lot going on here, but they're looking at 5-year intervals of population. Okay? They're looking at 5-year intervals of population. And so these are your intervals. So 5 years, this is after 5 years, after 10 years, 5, 10, 15, 20, 25, 30. So in this one, the change in x, as they give you, for all your changes in x, is 1. Okay, that's important. We've got to make sure they're all the same. When they subtract one from the other, they're 1. All right, and on the right, they went ahead and found your ratios. Basically what they did, what this part right here is just showing you the work, just like I did last time. So the first one is 56,767 divided by 56,225. So that one divided by that one. Okay. And they did that all the way down. So the next one is divided by the previous. The third one, kind of helps if I do this right. The third one is that one divided by that one. And they found all these ratios, but they're not the same, but they're all pretty close. You got 0.17, 0.2, 0.2.5, 0.25, 0.28, 0.25, 0.25. You got all of those. And so just like the linears, this is not perfect because real life is not perfect. So what we're going to do is we're going to find an average ratio. Now that's changed. We're going to find an average ratio. Okay? We want to find the average ratio. And what they do is they show you how to do that, which you already know. You add them up and divide by how many there are. So if I do 1.7 plus 1.2 plus 1.25 plus 1.28 plus 1.25 plus 1.25, and that's 1, 2, 3, 4, 5, 6. That's 6 of them. So add them all up, divide by 6, and I think they do it right below this. Give me just a second. They do. They get 1.23. They get that right there, 1.23. So from there, they take that as their common ratio, right? They average to 1.23, and they take their starting point. So remember, I gave you the equation y equals ab to the x. Well, in this case, a is starting point. So if we scrolled back up, we'd see that at 0, that's the starting point, 56,225. And we calculated our average ratio, and we're going to put that in for b. So this equation, while it's not perfect, because no equation is going to be perfect for this data, it is probably the best model that we can come up with given the data that we've got. All right? So that being said, we are going to move on and try example number 1.